Assalamu alaikum. So this is our week 3 part 2 video, and here we are going to discuss a few VHDL examples and how to use if statements in VHDL. Now, VHDL is a programming language. Actually, it's not only if statements. You can use switch statements, you can use loops, you can do all the things that we've done through C++. But in this class, I'm not going to go further. This will be our last part for VHDL. After that, I'm going to shift to actual computer architecture, which is the single cycle computer, starting from module number 2. But just keep in mind that this VHDL will continue with you within this throughout this semester, our 13 weeks of studying on inside the lab and lab discussions. So I'm just giving you here the basics. During the lab, Mr. Raya will go through with you throughout the semester and teach you all the needed information. So first of all, here we need to create an entity for a 2x1 multiplexer. Okay, we need to create a 2x1 multiplexer. 2x1 multiplexer, quite simple. 2x1, two inputs. I will call them I0, I1. We have one selector line and one output, which is what we are going to call it A. Okay, so this is the steps. It's called I0, I1, S0, and D. The output is D. First step, we need to create the circuit. This is our needed circuit over here. Now, this circuit, as you can see, we need 3 components: one AND, one OR, and one inverter. So first of all, we need to declare our entity. Our entity is I1, I0 as inputs here, these two. Let me clear. I1, I0 as inputs, S0 as an input, and D as my output, which is these 3 values. The next step, okay, next step is to call the components. Architecture structure of mux is. Okay, see these lines. First of all, if you remember in week 2, I told you that 2 dashes or 2 hyphens are considered a comment. So these are comments. These lines are just to make things look nice. So you can see here I have my entity, here I have my components, here I have my signals, and here I have my port mapping. So I'm going to call AND2, OR2, and inverter. Remember, all of these components need to be added in your project in the beginning. So after calling these components, you can say component AND2 is. You give the ports here and ports here. Next step is to call or declare your signals. I have N1, N2, N3 as my signals. So I will declare these signals. Once I declare the signals and give them a type, which is a standard logic, I start begin. After begin, I will do port mapping. Port mapping, start with the inverter. The inverter will take S0 and give N1. So inverter underscore 1, this is the name. It's of an instance of inverter. Port map S0, N1. Then AND, okay, and 2 underscore 1, which is this guy over here. Let me clear once more the writing. This guy over here, if we focus here, it will have I0, N1, give N2. I0, N1, give N2. The second one will have I2 and S0 and give N3. I1, S0 and will give us N3. The final gate, which is the OR gate over here, the OR gate will take N2, N3 and give us D. This is just using component instantiation. Of course, you can write the same program using a normal function by writing the digital form of this function. Now, simulating the circuit, we need to use a test bench, as you know. and from the test bench we create the signals KS, KP, and K and SS and WS. So this is our test bench. Again, test bench, remember, there is no inputs and outputs. It's just putting the full thing inside one entity called test bench, and inside the test bench you give your signals, which are the KS connected to should be connected here, K, P, and S. So this is the test bench for the warning belt. Okay, so your example here, it shows how you create your signals. You put the instances as we did earlier and simulate them and wait for the output and see when the warning will be active. So once more, a test bench entity has no inputs and outputs. Then you declare your component. You call the component which is belt warning. We call it K, P, S, and N and W. We declare our signals. We have an input signal connected to KS, an input signal connected to P, an input signal connected to S, and an output signal connected to WS. Then we begin by port mapping. Port map KS, PS, SS, WS. KS, remember the sequence, PS, SS, and WS, all of them connected. Then begin. We start giving them the signals and wait for 10 nanoseconds. And then we see the output waveform, which we are going to do in the lab, and see our output signal over here. Now, as you can see here, we had 3 inputs, so we had to create many outputs, which is 2 to the power 3, which is 8 different instances. If we want, we need to create here 8 different instances in order to have all the possibilities. So it's okay, but let's assume that you have 5 inputs, then you have 32, and then things become a little bit problematic, because the combinational circuit complexity will increase as 2 to the power n, and we have to create more and more test bench vectors. Usually we take samples, we don't create all the test bench vectors. So another example here, generate a process to compute the following: F is equal to AB or C complement, and G is equal to AB and BC. Sorry, AB or BC. So here you can see that A, B, and C and D are all inputs. Okay, we don't have D actually, so just forget this. Now you can see we start by creating a 2 output example entity. We call it any name. We call it 2 output example. It has 3 inputs, which is A, B, and C, and 2 outputs, which are F and G. Then we created the architecture behavior of this example. It has a process that is sensitive for A, B, and C. If any one of them changes, we start running. So we have A and B or not C. A and B or not C. And for G, we have A and B or not, this should be complement, okay, or not B and C. Okay, so then end process and end behavior. Quite easy if you follow this logic. Instead of drawing the circuits and component instantiation, this will give you the answers quite fast. Unless you are asked to do component instantiation, this is much more faster. So if we want to use an if statements, it's more or less like using if statements inside C++. So create a new entity that turns the warning light bells if car keys are in the ignition, indicated by K equal to 1. So this is if K is equal to 1, and the seat, the passenger is seated, indicated by P if P is equal to 1, and if the ignition, if the passenger seat belt is not buckled, then we have W, or indicated by S s is equal to 0. So there is another if statement. So we can do all of this using if statements. So you can see here, if k and p not s is equal to 1, see how the if statement, if then these brackets k and p and not s are equal to 1, this is our condition, then warning is equal to 1, else warning is equal to 0. Remember, if it's we start, you see here, an entity ends with an end entity, an architecture begin ends with an end behavior, a process ends with an end process, an f ends with an end f. Everything you start, you need an end statement for it. Everything you started, you need an end f statement with it. So for a 4x1 multiplexer, it's quite simple. 4x1 multiplexer, we discussed this earlier. We have 4 inputs, I0, I1, I2, and I3. We have 2 selectors, S0 and S1, and we have 1 output, which is D. So if S0, S1 is equal to 0 and S0 is equal to 0, then I1 is sent to D. Else if S1 is equal to 0 and S0 is equal to 1, then we go for I1 and so on. So this is using if statements. This also will make our life quite easy and simple. A 2x4 decoder. If you remember a 2x4 decoder, what is the function for a 2x4 decoder? So the 2x4 decoder, it has I0 and I1, and it has 4 outputs, which are D0, D1, D2, and D3. So here we have 0, 1, 0, 1, and here we have 0, 0, 1, 1. So 0, 0 will give us 1, 0, 0, 0. 1, 0 will give us 0, 1, 0, 0. 0, 1 will give us 0, 1, 0, 0. And 1, 1 will give us 1, 0, 0, 0. This is a 2x4 decoder. So you can simply do the function. So if I0 is equal to 0 and I1 is equal to 1, then 1, 0, 0, 0. Then 1, 0, 0, 0, and so on. Quite simple and quite straightforward. I think this is all for us today. This is the last part of module 1. So from here on, you continue with this Raya in the lab on VHDL. Each lab will have a different concept. So hopefully everything you can get it. Starting in module 2, I'm going to start with single cycle computer instruction sets. So hopefully this will be an interesting part in computer architecture. Hope to see you all soon. Thank you for watching this video and hope to see you all soon.